I remember the exact afternoon I understood what a nucleus actually does when it breaks apart. Not the headlines, not the newspapers, the real number, the one written in pencil on a scrap of paper, the one that made my hands go cold before I even finished the calculation. It was early 1939. A letter had come from Europe from a physicist named Niels Bohr, who had just arrived in America carrying news that most of us hadn't fully processed yet. Two chemists in Berlin, Otto Hahn and Fritz Strassmann, had bombarded uranium with neutrons and found something in the debris that made no sense. Barium, a lighter element, something that shouldn't have been there at all, not if the uranium nucleus had simply absorbed the neutron and stayed whole, the way every nucleus we knew of behaved. Lise Meitner, working in exile in Sweden, was the one who figured out what had actually happened. The uranium nucleus hadn't absorbed anything cleanly. It had split, torn itself into two smaller nuclei, almost in half, like a drop of water pulled apart by surface tension until it simply gives way. That word, fission, didn't exist yet. She and her nephew, Otto Frisch, borrowed it from biology, from the way a cell divides. Now here is the part that stopped me cold, sitting at my desk at Berkeley, with chalk dust still on my sleeve. When you add up the mass of everything that comes out of that split, the two new nuclei, the neutrons released, everything, it doesn't equal the mass of what went in. Some of it is simply gone. Missing, not lost, not misplaced, converted. And I already knew the equation that explained where it went. Everyone in this field had known it since 1905. E equals mc squared. Mass and energy are the same thing wearing different clothes, and the conversion rate between them is the speed of light squared. A number so large that even a tiny sliver of mass converted becomes an obscene amount of energy. I did the arithmetic that afternoon on the back of an old exam. The mass defect from a single splitting uranium nucleus, barely a fraction of a single proton's worth of mass, released roughly 200 million electron volts for one atom. One. A gram of uranium contains about 2.5 sextillion atoms. I didn't need to finish that multiplication to feel my stomach drop. I already knew what order of magnitude I was looking at. But the mass-energy conversion wasn't even the part that kept me up that night. It was the neutrons. When uranium-235 splits, it doesn't just release energy, it releases more neutrons than it absorbed. Usually 2 or 3 flying out from the wreckage of the nucleus, and each of those neutrons, if it finds another uranium nucleus, can trigger another split, which releases more neutrons, which can trigger more splits. Leo Szilard had already seen this coming years before Hahn and Strassmann's discovery, back when he was still thinking about it as a pure abstraction, a thought experiment he patented almost as a precaution, in case the world ever needed proof of who saw it first. He called it a chain reaction, and he described it to Einstein with the same unease I felt reading his letters. Not excitement, unease. A chain reaction means the process doesn't need to be fed from outside. It feeds itself. Every splitting atom releases the fuel in the form of neutrons for the next split. Under the right conditions, with enough fissile material packed close enough together, that reaction doesn't need a push after the first one. It runs on its own, faster and faster, doubling and doubling again in a fraction of a second, until the energy that comes out is no longer something you can measure in a laboratory, it's something you measure in a crater. I spent that spring doing the same calculation over and over, checking my own work the way you would check a bridge you're about to walk across. What is the critical mass? How much uranium-235? Packed into what shape, at what density before the neutrons stop escaping the surface faster than they can strike another nucleus? Below that mass, the reaction sputters and dies. Most of the neutrons just fly off into empty space without hitting anything. Above it, the reaction becomes self-sustaining. And past a certain point, it doesn't just sustain itself. It runs away entirely. The physics didn't care what I wanted it to say. It just sat there on the page, indifferent. Correct. What terrified me wasn't the mathematics itself. I'd spent my whole life comfortable inside mathematics, at home there in a way I never quite was anywhere else. What terrified me was watching an abstract, elegant idea about the structure of the atomic nucleus turn step by step, calculation by calculation, into something with an unmistakably practical shape. Physics doesn't usually hand you something that clean. Usually there's ambiguity, room for a theory to be wrong, decades before an idea like this could touch the physical world. This one didn't wait. Every experiment that followed only confirmed it faster. By late 1941, groups on both sides of the Atlantic had independently worked through enough of the numbers to know this wasn't a curiosity anymore. Enrico Fermi, a man I respected more than almost anyone alive, was already talking about building a pile, his word for a stack of uranium and graphite, arranged with almost obsessive precision, designed to let the chain reaction happen slowly, under control, instead of all at once. I wasn't in Chicago in December of 1942 when Fermi's team achieved the first controlled, self-sustaining chain reaction in human history underneath a squash court at the University of Chicago. But I heard about it within days, and I remember exactly where I was standing when I did. There was no explosion, no flash of light, just a set of instruments, a slow climb in neutron count, and a group of scientists watching numbers on a dial prove that the thing we'd only calculated on paper actually worked in the physical world. That's the moment the fear stopped being theoretical for me, not because anything had gone wrong, because everything had gone exactly right. Once you know a controlled chain reaction is achievable, the next question isn't really a scientific one anymore. It's an engineering one, and engineering questions get answered. How much material do you need? How pure does it have to be? How do you assemble it fast enough in the right geometry to go from below critical mass to above it in a fraction of a second? Because that's the difference between a slow, controlled release of energy and an uncontrolled one. I understood, sitting with those numbers, that we were no longer discussing whether this was possible. We were discussing how fast someone would get there first, and what shape the world would be in on the other side of that finish line. There's a particular kind of dread that comes from being the person who understands a piece of physics before almost anyone else does. You start seeing the shape of a machine that doesn't exist yet, built from principles you know are true, and there's no way to unknow it. I could see the outline of it long before there was ever a facility, a budget, a name like Los Alamos attached to any of it. The physics existed before the politics did. The politics simply had to catch up. What made it worse was how ordinary the underlying idea actually was once you understood it. This wasn't some exotic corner of theoretical physics reserved for a handful of specialists arguing over unobservable particles. It was nuclear structure, the same kind of physics that explained why stars burn, why certain elements are radioactive, why the periodic table has the shape it does. We'd simply found the one specific reaction in one specific element that released its energy not over millions of years like a star, but in a fraction of a second. I used to lie awake running the numbers differently, trying to find an error, trying to find some physical limit that would make the whole thing impractical. A purification problem that couldn't be solved. A critical mass too large to ever assemble anything. I never found one. The physics simply worked, cleanly at every scale I checked it. By the time I was asked to help organize the work that would become the Manhattan Project, I already understood something most of the men making the political decisions didn't fully grasp yet. This wasn't a bigger bomb. Every previous weapon in human history released chemical energy, the rearrangement of electrons around atoms, the same basic process as fire, just faster and more violent. This released energy from the nucleus itself, from a completely different physical mechanism, at an efficiency that made every earlier weapon look almost quaint by comparison. I remember explaining the mass defect to a colonel once, trying to make the scale of it land. I told him, if you could convert the mass in a single paperclip entirely into energy, it would be enough to power a city for a day. He didn't believe me. I didn't blame him. I hadn't fully believed it either the first time I did the arithmetic myself. We hadn't built anything yet. We hadn't assembled a single working weapon. But by 1942, sitting with those equations, I already knew, with a physicist's certainty, exactly what this would be capable of once someone finished the engineering. That's the part nobody talks about when they talk about the bomb. The fear didn't arrive with the explosion. It arrived years earlier, quietly in the space between one line of a calculation and the next. In the moment I finished checking the numbers and realized they weren't wrong.